Okay, hello guys. This is the fifth lecture. It'll be a relatively simple lecture in comparison to the third one and the fourth one, the dot product and cross product. So today we're going to introduce about the equations of lines and planes, in particular in the three-dimensional coordinate system. So let us do this. So first of all, let us do the line first. So a line in R3, or in a three-dimensional coordinate system, three-dimensional Cartesian product, in fact, that works for every dimension. So basically, a line is determined by a point and a directional vector. So suppose we're given a point, say R naught is given by X naught, Y naught, Z naught. This is in particular in a three-dimensional space, but it also works in every dimension. So given a point and a direction V, then you can construct any point on that line, in the sense that you can add this point by some constant multiple of this vector. So for example, this R x, y, z will be x naught, y naught, z naught, adding with a, b, c times something like 1 or 2 or minus 1 or minus 2. Okay. So basically, a line contains the information of two things, some initial point and some directional vector. If you only have a point, then there will be different orientations of lines, right? If you only have a vector, then you will have different parallel lines. So only when you're given a point and a vector, you have a um, solid definition for a line. Okay, a line is a point with a vector. A vector with a point is a line. So given a point and given a vector, how do we describe this line in terms of mathematical language? So we can do that in two ways. One is called a parametric equation. One is called a symmetric equation. So the parametric equation is basically what I just mentioned. You can give R, which is an arbitrary point, X, Y, and Z, is given by R naught plus V times T. So be careful, this guy is a vector or a point, depending on your notation. This is also a vector, where T is a scalar. So this is a scalar multiplication of this vector V. It basically means that how far have you traveled away from R naught. For example, this direction might be plus V, then this direction will be minus V and minus V. Okay, so you can write it in R equals to R naught plus VT, or in terms of coordinate, you have X naught plus AT, Y naught plus BT, Z naught plus CT. That is a definition of scalar multiplication and vector addition, right? And that holds for every T. A recorded notation is belongs to. So T belongs to R. So that means that you can have every different scalar scaling of that vector. You can do 1, you can do half, you can do root 1, you can do root 1,000, you can do log 2, you can do anything, any possible combination of numbers to this t here. Okay, and another way to represent this in a more cleaner format without a t is called the symmetry equation. So basically, this is just solving the parameter. What do I mean? You see that if I solve t here, you will get x equal to x naught plus, sorry, at. So x minus x naught is at. So t is equal to x minus x naught divided by a, right? And that is exactly a term here. So what we're actually saying is that this will be our parameter, t. Okay? So you see that this is also a clean format of representing a line because it contains the information that we just need. The point, x naught, y naught, z naught, and also the vector a, b, and c, right? So always remember whenever you're finding an equation of a line or vice versa, what you have to do is to find out the vector, the directional vector to be precise, and also the point, r naught, okay? And r naught and vector are invariant under some scaling. Sorry, that is not a good word. So what I'm trying to say is that R naught can be chosen to be any point on the line. It does not depend on the choice of R naught to give the actual formula for the line. And also ABC, the vector, is you can choose this vector up to a scaling up to a proportional vector. What I'm saying is that supposed to choose 1, 2, 3 for the line, then you should get some formula for 2, 4, 6. The scaling does not really, the magnitude does not really does not really contribute to the equation of the line. Only the vector direction contributes to the line. Okay, so now let's do some example. So the first problem here I said is to find the parametric and symmetric equation, so both representation of a line, passing through this particular point, 1, 2, 3, and minus 1, 0, 4. And I also asked you that when does this line intersect XZ plane? So don't forget that XZ plane is the plane where y is 0. So in terms of a three-dimensional coordinate system, x, y, z, this is the XZ plane, okay? It contains every point where y is 0. Okay, so as I mentioned, whenever you want to find a parametric, whenever you want to find an equation for a line, you always want to find a point and also the directional vector. So in this case, the point is already given. You can choose either of them. The directional vector is also quite simple. Since you have 2 points, then by connecting them, you will have a directional vector, right? And as I mentioned, that the scalar multiplication is not important. You can choose either this direction or this direction. It is up to a scalar of -1, right? So say we choose this subtract by this, you get -1, 0, 4, minus 1, 2, 3. That is -2, -2, and 1. Okay. So as I mentioned, you can choose either 2, 2, -1. You can choose 4, 4, -2, and so on and so forth. Those will all give you the same equation. So it is very flexible. Now we have our direction, we have our point, then you can just plug in the formula, right? So in terms of the parametric equation, you have the point 1, 2, 3 plus the directional vector together with a scalar multiple. And t is for every possible real number. You can also write that in terms of coordinate, then you get 1 minus 2t, 2 minus 2t, and 3 plus t. Right. And symmetry equation is actually quite simple. So you have x minus the x coordinate of the point, which is 1, y minus the y coordinate 2, z minus the z coordinate 3, divided by those directional vectors. You have -2, -2, and 1. And that is your there is your symmetry equation. Lastly, I asked you guys when does this line intersect the XZ plane? So basically, we're solving whether in this equation, so whether in this two equation, when is y 0. So for instance, if you solve this equation, you can get that y is 0 whenever t is 1, right? By plugging the parameter into the x and z coordinate, you will get your corresponding x and z. And in this equation, it's even more simple. If you plug y equal to 0, you will simply get 1 in the middle term, and you can solve correspondingly for x and z. So anyway, whatever you want to do with the parametric equation or symmetric equation, you always get the point to be -1, 0, 4. That'll be the point on the line and the XZ plane, right? So this will be a standard example of how you can solve the equation for a particular line passing through 2 points. Okay, this is not written in the textbook. I just want to collect this fact so you guys have a picture on how two-dimensional and three-dimensional lines are different. So we're interested in the relationship between two lines, whether they are parallel, they're intersecting, or whatever scenario happens. So in R2, actually you can write down the same formula for R2 in terms of either parametric or symmetric equation. I write it in this way so we can have a better presentation later. So say in R2, you have two lines, L1 and L2, given by A1x plus B1y plus C1, and the same for number 2, L2. And for R3, you have, I written down here in terms of the parametric equation. So P1 plus B1t, P2 plus B2s. Okay? So what are the scenarios between these two lines? What are the possible intersection configuration of these 2 points? So first of all, they might be the same. So same means that they're exactly the same line. They lies on the same trajectory. So for example, in L1, in R2, and in R2, the two lines will be same whenever one is a scalar multiple of another. So in the sense of the coefficients, you have A1 divided by A2 equals to B1 divided by B2 equals to C1 divided by C2. So basically, I'm just saying that they're a scalar multiple of each other. Say you have 2x plus y plus 3 equal to 0. You can multiply that by 2, and this will be the exact same line. Okay. And in terms of R3, one thing to note that is that you always have V1 parallel to V2, right? In order to make that the same. So again, V1 parallel to V2 basically just says that these are scalar multiple to one another. And I just mentioned here that another thing to check is that P1 belongs to L2, or P2 belongs to L1, depending on your choice. So what that means is that simply V1 parallel to V2 only ensures that L1 is parallel to L2, something like this. But to make them actually touch together, you have to make this point belongs to this point, this line, or this point belongs to this line. And they will happen simultaneously given that they're parallel. Okay, so that's the criteria on how to determine whether two lines are the same. And to determine whether two lines are parallel, then as mentioned, the directional vector or the coefficient between x, y are the same, but you have different constants, C1 and C2. And again, the same thing happens here. So we have parallel directional vector, but the corresponding point does not lie down one another lines. So they will be parallel instead of the same. Okay. Now, when those two lines intersect the point, so it is in this case, it is either when the slope is not the same. So A1 divided by A2 is not equal to B1 divided by B2. And that means that you will always have an intersection whenever two lines is not parallel. However, this is not the case for three-dimensional lines. So in a two-dimensional line, the simple condition of V1 not parallel to V2 does not ensure that these two lines are intersect. So we will see this afterwards, but basically that's because whenever you are solving this equals to this, you actually have three equations, right? Because V1 contains three components and V2 contains three components. So you will have three equations against two variables T and S. That makes things a little bit more complicated. That the system might not be solvable. You have more constraint than your variable, so that makes the system unsolvable for some particular coefficients. So I'm saying that you have to have V1 not parallel to V2. That is quite trivial. Otherwise, you will either be the same line or a parallel, right? And we have to be having R1 T equals R2 S solvable. That means that they actually have an intersection, right? And the last scenario is something that does not happen in two-dimensional space. So we already know that in two-dimensional space, whenever the vector is not parallel, the slope is not the same, then you always have an intersection. But as I mentioned, there might be a different situation in R3. So if the two directional vectors are not parallel, it's also possible that this is not solvable. So if it's not solvable, then it is skewed. And to be precise, how that figuring looks in the coordinate system, it looks like this. Okay, they're not parallel. They have different directions, and they actually just not intersect one another. Okay, and that only happens in the three or more dimensional space instead of two-dimensional space. So this is a strange situation which does not happen in our usual Cartesian plane. Okay, now let's do some example of that skew line. This will not be entirely important in our lecture because we won't be encountering this a lot in our calculus course, but I just put this here to be for completion. So let us define these two lines. L1 equals to 1 minus 2, 4, 1, 3 minus 1. L2 to be another line defined in the three-dimensional space. So first of all, we can see that these two lines are actually skewed. First of all, obviously they have different, not parallel direction vectors, right? So they either intersect or they're skewed, right? Those are two different scenarios. Okay, so we see that if we want to solve L1 equals L2, you will see that you have these three equations, and as we mentioned, you can perhaps solve the first three equations to get a solid T and S, and then you can try to plug this back in the third equation. In this case, it does not really solve the equation, so that means that you cannot find a pair T and S let's solve these three equations. So those two lines are not intersecting. So they're skewed in terms of our fancy new word. And now I ask you to find a distance between these two skewed lines, right? So how do we do that? There's multiple way to do this. Let me try to here to introduce one way. So first of all, one way to do this is that you can grab something here. So this is a vector that is both orthogonal to L1, sorry, to the directional vector of L1, in this case I denote by V1, and the direction of V2, right? So this direction is actually quite easy to find. You're trying to find a vector that is orthogonal to both vector. And that is directly a definition of cross product, right? So we can do the cross product between V1, which is here, and V2, which is here. And you get this thing. So the red direction has the directional vector being this vector here. And how is that useful? So if you have this guy, and if we connect any point P1 and P2 on this two line, then if we project this green thing onto that red line, you have the distance, right? So basically, let us try to find any point on the line. In this case, I just choose the definition, so this point and this point. Then you have P1 and P2. And then now we project that thing onto the vector 13 minus 6 minus 5. It does not depend on what the magnitude of that vector is. So the distance between these two lines will simply be the magnitude of the projection of P1, P2 onto V3. Okay? And then by definition, it is P1, P2 dot V3 divided by its magnitude, which gives us 8 divided by root 230. Okay? I encourage you guys to try different P1, P2 and different V3. So V3 is okay up to a scaling, right? You can always scale this factor. And P1, P2 is okay up to a different choice of points on L1 and L2. And you should always get the same projectional vector up to direction. But the length will always be the same. So try to do that to convince yourself that this choice is actually really flexible. Right, so there we determine a way to find a distance between two skew lines. Right, now we're over with the line. Let's do some plane, which is not a particularly interesting object in two-dimensional space, but a very interesting object in three-dimensional space. So actually, just like the point, a plane is also determined by a point. Just like the line, a plane is also determined by a point and a vector. But in this case, we're not trying to find the directional vector, which is not really definable. We can, on the contrary, define the normal vector. So how does that work? Given a point, you can see that any point on that plane connected with the initial point we chose or not is always orthogonal to some vector, right? Some common vector, in fact. So given that vector and given that point, then we can collect any point that after connecting to R naught is orthogonal to N. And that will be our collection of points of the plane, right? So simply follows from the definition, you have the equation for the plane. Given a normal vector and given a point, then the equation is simply N dot R minus R naught is 0, where R is just our arbitrary point XYZ. And you can definitely write that in coordinate system. So you have A, if N is ABC, and R naught is X naught, Y naught, Z naught, then you simply have AX minus X naught plus B Y minus Y naught plus C minus CZ minus Z naught equal to 0. Okay, so that's one way to represent a plane. And we don't really have a kind of like a symmetric setting up for this kind of equation. So this will be the only one that we use. The vector product kind of equation. Okay. All right, now let's jump into the examples. So in this case, similar to the line, I want you to find some plane that pass through these 3 points. 1, 2, 0, minus 2, 1, 3, and 5, minus 2, minus 1. Okay. So just as in the line, the only information that you have to know about a plane is a particular point, which in this case we have 3, so that's really nice. Another thing is a normal vector. Now, how do we find a normal vector in this case? So as we mentioned, any vector that lies on the plane is actually orthogonal to n, right? In this case, you can find, for example, PQ and PR. And to find a vector that is orthogonal to those two vectors, by definition, you can do the cross product, right? In this case, you get 13, 9, 16. That is orthogonal to both of these vectors. So we can choose either point for our initial point and use this normal vector to generate the equation, which is normal vector taking inner product, taking dot product together with xyz minus some point. In this case, I choose 1, 2, 0, will be 0. And you can do some algebra and arrange it into this format. Okay, so just memorize this. Whenever you're finding a line, find the initial point and find the directional vector. Whenever you're finding a plane, find the initial point and find a normal vector. Okay, with whatever technique you have. After that, you have every information that you need. All right, this is a second interesting equation exercise. So first of all, we want to find an angle between these two planes, 2x minus y plus z equals 4, and this guy. And secondly, I want you to find a symmetric equation at the line of intersection of these planes. So two planes intersect at one line, right? And you can ask about the equation of that line. So first of all, let's see how we can extract the information of normal vector from an equation here. Let's go back here. You can see that actually the normal vector is hidden in the parameters, in the coefficients of x and y and z, right? A, B, C is exactly the normal vector n, right? So for example, in this case, the normal vector is simply 2, minus 1, and 1. 2, minus 1, and 1. And in this case, it is minus 3, minus 2, and 3. How does the normal vector help us finding an angle? So you can see in my picture here, I try to draw this precisely. You have two planes, E1 and E2. Now if you draw the normal vector, then E1 have this direction, right? E2 have this direction, the normal vectors. You can actually see that the angle that E1 and E2 have is of the same angle together with the normal vector N1 and N2, right? And in some sense, it might be simpler to seeing in this way. If you put your eyes here, you can see that these are the two planes, theta, E1, E2. Now, if you draw the normal vector, this is a normal vector for 2. And this is a normal vector for 1. So you can see that these two should actually be the same because basically they're just a translation of this direction by 90 degrees, right? So we conclude a very important concept, which is that the angle between the normal vectors of two planes is the same as the angle between those two planes. So to find the angle between two vectors is very, very simple, right? We have done this 100 times. You can use the definition for dot product. So theta will be inverse cosine of n1 dot n2 divided by their corresponding magnitude. And then it's just the algebra, which you get 95 degrees. Okay. Now, for the second thing, we want to find a symmetric equation of the line of intersection. So as I mentioned, you have to find the point and also a directional vector, right? In this case, directional vector is actually quite simple. So you have this direction, which is what we are interested in. And this is fortunately orthogonal to both the normal vectors, right? So again, you can compute the directional vector through computing the cross product of n1 and n2, the two normal vectors, which you get this vector. And so our last job is to find some point that lies on the line, which is a point that satisfies both equation E1 and E2. So you can solve that quite simple. You have two equations with three variables, so everything is very flexible. For example, in this case, I set z to be 0. Then you have two equations with x and y, and that is quite easy to solve. I won't present the details here. You can simply plug any point that you want whenever they're on both of these planes. Okay. So given now the the directional vector, and also the point, you can, in this case, I write symmetry equations. X minus the point, y minus the point, z minus the point, divided by the directional vector coefficients should be the same. Okay. So another takeaway about this is that the line of intersection between two planes always have the direction of the cross product of the two normal vectors of the plane. So V will be parallel to N1 cross N2. Okay, now let's do the kind of the converse problem. So given two lines, in this case L1 equal to this guy, L2 equals to this guy, I want to find the point where these two lines intersect. And that is quite simple. You again try to solve the equation, and fortunately there is a solution, 202. So that means that those two lines are not skewed, but actually intersect. Now, just as we mentioned before, this is a converse problem, so we want to solve the equation of plane that contains both lines. Previously, we are solving a line that is the intersection of two planes. Now we're solving the plane that contains these two lines. And again, you see that the normal vector is actually orthogonal to both of the directional vector, right? So if this is V1, this is V2, then this will be our normal vector, or this depends on your orientation. But anyway, the normal vector will be parallel to the cross product between V1 and V2. That's what I'm trying to say. So you can again find the normal vector through taking cross product, and that gives you this thing. Since we already have some point here, right? So you can use our definition for the plane, which is the normal vector taking dot product with xyz minus a point is 0. And doing some algebra, you get this nice equation. So you see kind of an analogy between these two problems. In this case, the line of intersection will have the directional vector that is parallel to the cross product of the normal vectors. In this case, the normal vector will be parallel to the cross product of the two directional vectors. So try to familiarize yourself with these two concepts. This is two very standard problem about lines and planes. Now, I think this is just, yeah. So for our last example, I want you to investigate distance between a point and a plane. So I think we have investigated the distance between a point and a line in the third video, the dot product. So now we're doing a different approach, which is finding a point, the distance between a point and a plane. So I claim that given the plane being ax plus by plus zz equal to d, then for any point p x naught y naught z naught, the distance between that point and the plane is given by this formula. So in the numerator, you simply plug x naught y naught z naught into that equation, and you take absolute value. For the denominator, you're taking the magnitude of the normal vector, a squared plus b squared plus c squared, right? 2 is simply a exercise about how to use the formula. So let's try to prove the first formula first. So this is our kind of figure. You have a point P, you have a plane here, and the way to find a distance, the blue distance, is quite simple. So you see that as I draw, you can find any point Q on the plane, and then you project that onto the normal vector. That will be a corresponding vector that we're interested in, because if you find out the distance, the magnitude of that vector, then you can have the distance between a point and a plane, right? So as I mentioned here, the distance between, actually, let me name this E. So distance between the point and the plane will simply be the projection of, in this case, QP, or yeah, QP X. Oh, actually, yeah, I should draw this in another direction, but anyway, it's okay if you use this direction or this direction. It will all be the same, because we're only interested about the magnitude. So you see that in this case, QP, if I set Q to be x1, y1, z1, then QP will be x naught minus x1, y naught minus y1, z naught minus z1. So if you recall in my proof of the distance between point and a line, I choose an actual Q, right? I choose something like 0 minus b over c or something like that. And actually, we can choose that to be an abstract point, which means that I'm not actually specifying x1, y1, and z1 as a function of a and b and c. We will see that soon enough why that is the case. So this is the vector given here, actually given here. This will be the correct direction. And we are taking dot product with ABC divided by the magnitude of that vector. So that is our actual formula. Now let us try to reduce it, because we don't know what is x1, y1, z1, right? So if I take everything in account, I will have ax naught, by naught, and cz naught. And now I'm subtracting that thing by, sorry, I keep doing typos here. This should be x1, y1, z1, my bad. So it'll be ax1 plus by1 plus cz1. Now, given the fact that x1, y1, z1 actually lies on the plane, that means ax1 plus by1 plus cz1 plus d is actually 0, right? That's the definition of being on the plane E. So that means that this guy here is actually minus d. So you're subtracting minus d, giving you our desired formula. So you see that it's really nice that you don't have to choose a particular point x1, y1, z1. As long as it lies on the plane E, you always have this nice relationship. And you can do the same thing for the distance between point and a line. You can choose arbitrary point x1, y1 on the line, and you do a projection. Then by definition of a line, you can always reduce the quantity, something like x1 plus by1 equals to negative c or something, right? So bottom line, we always know that the distance between a point and the plane is given by this nice formula. Okay, and this is just a simple evaluation exercise. You plug this point P and this plane E into this equation. And note that I have to move the 5 here to make things consistent. It should be ax plus by plus cz plus d equal to 0. In this case, that d is equal to minus 5. And the rest is just algebra. You get 18 over 7, 18 over 7 is the distance between the point P and the plane E. And we just want to recall here that we have this similar formula. The distance between a point and a line inside R2 is given by x naught plus by naught plus c divided by the corresponding normal vector a squared plus b squared taking square root. Right? Okay. So let's do a quick review. There is not many concepts going on, so we simply introduce how you present a line, which there are two different format. One is a parametric equation, one is a symmetric equation. We also introduced the presentation of a plane, which only relies on two information. One is the initial point, and one is the normal vector. And then it is just different examples and exercises. So bottom line is that to find out any information about a line, you have to find out the initial point and the directional vector. To find out any information about a plane, you have to find out the initial point and also a normal vector. Okay, and there are obviously different type of problems interlacing lines and planes, which I have presented here. So in this case, I would recommend you try to do more exercises in your textbook because those are the important stuff. You want to figure out how to extract information from an equation of line and plane, or to derive the equation through some information of a line and plane. That's like the basic concept of what we're doing here. Okay, so now we're sort of finally done with the three-dimensional geometry. I will see you guys in the next video, which will start dealing with functions, and that is the core of this course. See you.